This meeting is being recorded.
So welcome everybody. We have the great privilege today to hear from Dr. Kate Brand. Kate is a magnetotelluric specialist. She's from Australia and has worked at the Geological Survey of South Australia for a while, has done a whole bunch of MT surveys all over the place, and has actually recently gotten a job doing something very different, working for space weather for the Australian federal government. So this is one of our last chances to get to hear from Kate about all of her wisdom regarding sort of the magnetotelluric method and how you can do imaging of the lithosphere with it. So we're very glad that she's with us. It's very early in the morning for her over in Australia, so we're very grateful that she was willing to wake up super early and talk to us. And without further ado, the floor is yours, Kate.
Great, thanks, Dan. Hi, everyone. It's great to have the opportunity to talk to you all. I'd like to acknowledge all the co-authors from this work. I have tried to do that throughout my slides, but I'd particularly like to highlight Dr. Stefan Thiel, Professor Graham Heintzen, and Ben Kay, who have helped and done a lot of the work as well that I'll be presenting today. For any particular acknowledgements of material, if you need to follow up on anything, just send me an email afterwards and I can send that through to you. So this week in Australia, it's National Reconciliation Week. So I'd like to just begin by acknowledging the traditional owners of the land from which I present to you from today. So I'm in Adelaide, South Australia, which is the lands of the Kaurna people. I'd like to pay my respects to elders past and present. So as Dan mentioned, I have had a little bit of a career change since receiving this invitation. So I was at the Geological Survey of South Australia, so working in the state government, with the role of sort of helping out with mineral exploration and better understanding sort of mineral systems. And I'm now at the Bureau of Meteorology in the Australian Space Weather Forecasting Centre. So that's the equivalent of your Space Weather Prediction Centre in NOAA, if you're aware of that facility. So I'm about 6 weeks into the job, and yeah, it's very exciting so far. It's great spending time learning about space. So today I'm going to talk to you a little bit about the transition to net zero and why that means we would need sort of more geophysics rather than less, which, you know, perhaps may be a public perception that as we're moving to a greener future, we're going to need to extract less resources from the ground. Then I'll talk a little bit about lithospheric scale understanding of a mineral system, how magnetotellurics can help, and a brief sort of overview of the evolution of MT in Australia before giving some case studies for mineral exploration and just understanding the lithosphere. So just to start with a graph, focusing on the increased demand of copper for the energy transition. So this is over a decade from 2020 to 2030. And what it's showing is the increased demand that's anticipated for various different sort of clean energies. So there'll be increase in copper needed for power grids from 1.7 to 2 million tonnes. For EV batteries, 210,000 tonnes to 1.8 million tonnes. Huge jumps. So you can see that the need for copper is certainly not going to be going away. And the same can be said for a lot of different minerals. This graph here shows that we don't, you know, with the current minerals and resources that we don't have an endless supply. And sorry, when I say have, the ones that we know where they are and how to extract them. And you can see the green section in the middle, which is based on renewable energy minerals, just a small selection of them. You can see that by sort of 2030, 2040, there's not going to be much left with the exception of rare earth metals, and there's our copper supplies aren't great, you know, 2050, 2040. So we need to keep finding minerals. So sort of focusing on this Australia region, to have a look at the percentage or the amounts that we have of each of these different reserves as a percentage of the world reserves. So we've got quite a lot of lead, zinc, silver, gold, copper, and a bit of coal. And just for your own interest's sake, I've done the comparison for North America, if you were curious. So obviously a lot of coal, uranium gas, lead as well, and some of the standard base metals. So in Australia, we have a problem though when it comes to finding more mineral resources. So discovery rates are severely declining, as they are in many places in the world. In Australia, we've got 70% of the continent is under sedimentary cover of some degree of thickness. And so this map is coloured by the cover thickness, and then the circles are the deposits and their depth of the deposits. So you can see the yellow and the white deposits are the very shallow ones, and you can see there's quite a lot of those, particularly the yellow ones. And then as we get to the deeper deposits, 200 meters or more, there's very few. And it's very rare that these deposits are found in the green or the blue regions where you've got cover thickness of 500 meters or more. And even the yellow ones, there's not too many there. So we need to develop better ways to explore undercover. Traditionally, a lot of mineral exploration is done with the tools on the left-hand side of this sort of explorer's toolkit. So geological mapping, drilling, which is of course expensive, potential field methods, magnetics, gravity, reflection seismics, and probably with the exception of gravity and reflection seismics, it's hard to get sort of deep information from these techniques. So looking at the Earth in a very simplified view, when we've got the barren cover over the top, we've got the mineralized rock beneath. The top-down shallow techniques can sometimes struggle to get through that barren cover. But luckily for us, the mineralized rock can be associated with deeper pathways, and that's where the sort of bottom-up deep imaging can come in, using approaches to image those pathways. Why those pathways are there, this is just sort of one example which shows the way sort of the full lithosphere can be affected in the genesis of mineral deposits. So this is from a paper by Bill Griffin and co-authors in 2013, showing a plume impinging on subcontinental lithospheric mantle. And you can see that this plume event has created refertilization of a depleted lithospheric mantle. And then sort of high degree melting, which is occurring up the sides of the cratonic region. So the magma would find the path kind of least resistance, the weakest sort of path, and that tends to often be at craton boundaries. You can see above that we've got a nickel copper deposit, and you would be able to image this deep pathway. And just a couple of other deposit styles showing, I guess, the deeper signatures of the formation. So copper porphyry in an arc setting, VHMS in a back arc, orogenic gold. Each of these are associated with sort of fluid and magma transitions up through the mantle or within the crust. So looking for just this star might be difficult, but seeing the bigger sort of picture may be a bit easier. And just an example from the Western US. So this is P-wave velocity at a depth of 90 kilometers, where the hotter colors are the more the lower velocity, lower velocity, the cratonic regions. And you can see the yellow dashed lines are sort of outlining those cratonic regions. And the mineral deposits all tend to occur kind of on the edges of these sort of more cratonic, the older block regions, as opposed to in the middle of them. So this is a global study that shows sediment-hosted base metals, so lead, zinc, and copper, published in 2020 in Scientific Reports. And the map here is coloured by the lithospheric thickness. So the red regions are very thin lithosphere, the blue are thick lithosphere, and the white is about 170 kilometres thickness, and that's kind of a bit of a sort of transition region in this study. And so what the results of this study found is that 85% of the sediment-hosted base metals are used in this study, and so they're all shown with the various different symbols and they're coloured by deposit age. So 85% of those occur within 200 kilometres laterally of this gradient in the lithospheric asthenosphere boundary. So at the white region, so within 200 kilometres of any of these white regions is where 85% of the sediment hosted metals occur. So just using lithospheric thickness criteria alone on a global scale, you can reduce the search space by 50%. And this is just zooming in on Australia. And so within Australia, we've got the thicker, more cratonic regions of Australia on the western 2/3 and the thinner on the eastern third. And you can see sort of at that gradation, we've got these sort of major deposits. So then to be able to image these, we need to move to the tools on the right-hand side of the toolkit. So these are the deeper imaging, so geochemistry, where rocks are available to get that information, seismic tomography, and magnetotellurics. So magnetotellurics is going to be the focus of the rest of this talk. So MT as a lithospheric scale exploration tool. Most of you will be aware how the magnetotelluric technique works, and probably more in a marine environment, being based at Scripps, but we do collect it on land, with the caveat being that we have to actually dig holes on land as opposed to just throwing it over the edge of a ship. So we've got the natural source from the sun, from solar wind. We've got lightning strikes occurring, and then we're measuring the electric and magnetic fields from the currents induced in the earth. This is kind of representative of what quite a lot of Australia looks like, and it can be quite difficult to get to parts. So you can see we've got a helicopter there for that. So the mineral system, as I mentioned, has this sort of fluid delivery pathway. So we've got the ore deposit site that can be very difficult to find. So Graham Heinzen refers to this part as the needle, and then the fluid delivery pathway is the haystack. So instead of trying to look directly for the needle, why don't we start looking for the haystack? And so that's where magnetotellurics can come in. We've got a broadband MT that can image sort of the top 50 kilometres or so, and long period MT down to several hundred kilometres. So this is probably the most famous example of magnetotellurics in a mineral context. So it's now sort of commonly referred to as the fingers of God. And so we've got this big conductor, 15 kilometres and deeper, leading up to 3 different deposits. So OD is Olympic Dam, which is the world's largest uranium deposit. It's an iron oxide copper gold deposit as well. So it's the 4th largest copper deposit in the world. And WW Werder Well and Vulcan are also IOCG deposits. So you can see these pathways coming up from the deeper conductor. This is a very busy slide, which I'm actually not going to go into in any detail, but all I wanted to do was draw your attention to a brand new paper out maybe a week or so ago, so new that I haven't yet had a chance to read it, but I did just want to make you aware that the study exists in case it is of interest to you, where they're looking at correlations of resistivity with mineral deposits on a bit of a global scale. So obviously as an example from the US array and from AusLAMP down here, but the results showed that 90% of orogenic gold occurs within 26 kilometres of 100 ohm meter contour. So the 100 ohm meter is again the white contours in this. So here we're looking at resistivity, whereas in that other study we were looking at lithospheric thickness. So they had some great sort of statistical correlations between orogenic gold, porphyry copper, and BHMS. So I will, I guess, obviously talk about Australia for the rest of the talk. So just to give sort of a very brief geological overview, I've mentioned the western 2/3 is the older cratonic parts of Australia. So with the Western Australia, Northern Australia and Southern Australia cratonic regions, and sort of some origins throughout and sedimentary basins. And then the eastern third is the Phanerozoic part of Australia. It's got the Tasmanides, which is a series of orogenic events that have accreted onto the eastern part of Australia starting around 510 million years ago. The area I'll be focusing on mostly is around here. So we've got the Gawler Craton, which is a huge part of South Australia and where most of the mineralisation in South Australia is. We've got the Konamuna province and the Flinders Ranges. So the Konamuna province is Paleo to Meso-Proterozoic, and then we've got the Neo-Proterozoic Flinders Ranges in between. So these two regions were thought to be connected prior to rifting and then the subsequent formation later of the Flinders Ranges there. So we've got a lot of information, great geoscience information across Australia. So geophysical maps, geochemical, surface geology, drill holes, and so the next question is, where do we stand with magnetotellurics? So just very briefly reflect on where we've came from. So this is one of the earlier studies, definitely not the earliest, along the magnetotellurics line. This is actually geomagnetic depth sounding though. So this is where we're only measuring the magnetic field rather than the electric field as well, which means that we can get reasonably good lateral constraints, but not very good vertical constraints, or we can also resolve sort of relative trends in the conductivity, but not the absolute values in resistivity very well. So this is sort of 500 kilometre spacing across the country. Some of the, one of the earlier interpretations was this huge sort of conductive zone across most of Australia. Thin sheet modelling was done of that. I won't go into detail on that. And then eventually in 2014, a 3D inversion of this data. So this leads us to kind of what our best understanding of the conductivity of the whole of Australia was. But as I mentioned, it's got all those caveats with the fact that it is very low resolution, but still it is a really lovely map to have of Australia. But there was obviously room for improvement to increase the resolution and add full magnetotelluric sites. And that led to AusLAMP, the Australian Lithospheric Architecture Magnetotelluric project, a similar sort of concept to the US array, looking here at 55 kilometre site spacing. So this is on every sort of half a degree on the grid. So overall, it will be 2,800 long period MT sites. We leave them out for 2 to 3 weeks. And we're in about, it says 10th year, but I think we're in our 9th year and about halfway complete. So the purple and the red are complete. This is a huge collaboration. So between universities, so Adelaide University was one of the starters of this project. Geoscience Australia has done a huge portion, and state government geoscience agencies as well, including the Department of Energy and Mining, where I was recently working. Ignore the black triangles on this, that this is the MT sites. It's a little bit out of date, but again, I just wanted to show the model that we had in 2014 from the national grid of the geomagnetic depth sounding. And I've just done a very crude job of pasting the new sort of models onto Australia, just to show, if I flick back and forth, sort of that increase in resolution that we get. So when this is complete, this is going to be a really exciting data set. And of course, as well, when we can do a model sort of this continuous region too, will be really fascinating. So it's a new map to add to the data set there. So the beauty of doing a survey where you're visiting every 55 kilometres on a grid means that you end up going to some locations that probably not many people have been to before, but are very special. So these are just a few photos from my trip. I could probably spend 40 minutes doing a slideshow just on photos, but I'll just leave a couple here. And on my next slide, I've got a video just showing what some of the land looks like that we acquire the data in. Okay, forgot to share my sound, but this is very typical country with the dunes, lots of bushes. yeah, it's very beautiful. One way to look at the data from AusLAMP is using induction arrows. So these point towards in the direction of increasing conductivity. So you can see within the Gawler craton, this is sort of looks like a bit of a pin cushion. So it's all the arrows are pointing out towards the edges, which hints that there be some sort of conductive regions through here. And you've got where the arrows are sort of pointing in opposing directions. That's where you'd see these sort of major conductivity features. You've got a lot of arrows pointing towards the ocean, which is the effects of the conductive ocean. But to jump into a couple of models, these have been around for a while, so you might have seen them, but I've just got a couple of slides. So this is a 30-kilometre depth slice, so the red regions are electrically conductive, the blue are resistive. So this is a map of the lower 2/3 of South Australia. And the dots are copper. So the red, the maroon dots are copper occurrences. So just sort of a small amount of copper has been observed, and the blue are actual copper resources. So they're probably the more significant ones to be looking at. But you can see that they're all occurring on these regions of lower crustal conductors. So showing that, you know, there's these signatures beneath these deposits that we can still see today. And this one, this is the same depth slice, just plotted in different software. But in green, we've got the mines and projects. So this is an interesting as well to see that there's a huge variety of different mines occurring, but still almost all of these seem to be occurring where these conductive regions are. And this is showing a conductive isosurface of the major conductors. So you can see this is the Flinders Ranges coming through here. This is the Gawler Craton in the Konamuna province. And you can see this sort of conductor going all the way around the Gawler Craton, couple through the Flinders Ranges, and you can see this sort of deep connections as we spin around there. So now I just want to move into some case studies. I've got 3 or 4 to show, but we'll see how many I get through in the time that we've got. So this first one is based on the Delamerian Origin region, a photo from fieldwork, and this was a collaboration by Geological Survey of South Australia, Geoscience Australia, the University of Adelaide and AusScope. And the study area is shown here, so you can see on the top right where it is in context of Australia. So the black outline is the outline of the area that was impacted by the Delamerian origin. So this was the first origin in a series of orogenic events that I referred to as the Tasmanides earlier. So this was covering all of, affecting all of this region here. And so we've taken AusLAMP data from eastern South Australia, from Western New South Wales and Western Victoria, and modelled it all together. And we've got 400 long period MT sites here. So this is probably one of the biggest models done with AusLAMP data sets so far. This is again just showing this study area, and we've got the outcropping geology of the Flinders Ranges. This is the Nakara arcuate feature coming down here. And here we've got an area that's covered by Murray Basin thick sediments, so not too much is actually known about this area. So having a look at the model, so this is, I'll show you just a couple of depth slices. This is a 20-kilometre depth slice, and you can see that there's, you know, a lot of sort of heterogeneous conductivity. I'll talk about a couple of the more major features in later case studies, but you can see, you know, we've got Eyre Peninsula is very conductive, the Konamuna province is very conductive. The area that I want to focus on is kind of through here. And these white circles are the location where we've done an infill MT transect of broadband sites, so 1.5 kilometre spacing instead of 55 kilometre spacing. So that enabled us to have a huge increase in resolution. So that's, we're going presumably around this sort of areas where we're going from the older parts of South Australia into sort of the Cambrian rocks through here. Going to a 50-kilometre depth slice, you can see this transect is kind of on that transition in resistivity. The yellow dashed line sort of joins this kind of conductive region. And you can see with the stars, we've got various different deposits. They're coloured by their style, deposit style. And the really interesting thing here is that, what we might have expected is that this trend would continue down and wrap around, and would wrap around down through here, which, if you remember from the map that had the surface outcropping geology, that the trend was down like this, and that's a trend that you see in magnetics and gravity as well. But instead what we got is this conductor that extends straight through here. These deposits, I've mentioned they vary in style, but they also vary in age. So from the Broken Hill deposit, which is 1.8 billion years old, lead, zinc, silver deposit, hillside and iron oxide copper gold deposit, and then deposits through here which are thought to be much younger, and we'll talk about a little bit more after. So it seems that we've got this sort of upper mantle or lower crustal conductor that's connecting all of these deposits. I might just skip over that video. And this is having a look at both the AusLAMP results and the crustal transect. So this is using ISO surfaces. So anything more conductive than 50 ohm meters is coloured in pink, and more resistive than 5,000 ohm meters is in blue. And you can see that, so this blob at the bottom is from the AusLAMP model. We've cropped the AusLAMP model at a depth of 10 kilometers or so. But this conductive feature extends, that's that long linear feature that it would extend like that. And you can see that sort of from that deeper conductor, we've got these pathways that are coming up. And here we've got in dark blue, this is the Anabama Pluton. That's aged just under 500 million years old. And you can see that this conductor sort of snakes up and around this Pluton. So that suggests that this pathway must be younger than the Pluton. And so we've got this long linear-ish conductor, the deeper conductor, and then from there we've got pathways coming up that appear to be younger. So you've kind of got a series of different, we can assume that with this area that is being tapped at a certain point in time, the mantle feature below is being tapped, and perhaps for other deposits that might occur at a different time. So this is sort of a cartoon version of that previous image. We've got where these pathways come up. This is the Anabama Pluton, the granodiorite that I was talking about, the really resistive region. And here we've got a copper molybdenum porphyry deposit, copper gold molybdenum, and where the other conductive pathway comes up, we've got long strike, some gold deposits as well. So you can see that it seems like these are connected, which previous sort of fluid inclusion studies in these two deposits had suggested that as well. So that's really interesting. Moving on to the next case study. So this is the Konamuna Cube project. This is run by University of Adelaide by Graham Heintzen, Ben Kay, AusScope provided the funding and instrumentation, and at the Geological Survey and at Geoscience Australia, we supported that. That was out acquiring some of the data for the Konamuna Cube. So the Konamuna province, this is the region that I mentioned was thought to perhaps previously been connected directly to the Gawler Craton. So the Gawler Craton has a lot of major mines, and you can see these the stars. So that these are the major IOCG deposits, with Olympic Dam, the one that I mentioned is the world's biggest uranium and fourth largest copper deposit. And they're red. These IOCG deposits are associated with the intrusion of the Hiltebur Suite 1595 MA, which is the dark sort of red regions. And in the Konamuna province, you've got sort of very similar rock packages and kind of a lot of prospectivity for that region based on its association with the Gawler Craton. So the Konamuna Cube is basically taking the conductive feature that you saw in my previous Delamerian model, where I said the Konamuna Cube, the Konamuna province was quite conductive. And so we've got the 50-kilometer spacing from AusLAMP, and then the Konamuna Cube is these the black grid, not the black transects, that show we've done 25-kilometer spacing. So just to improve the resolution, and there's going to be a passive seismic acquired at those locations as well as heat flow data too. So once complete, it will be a really fascinating data set, but I'm just going to briefly show some results from the modeling so far. So this grid is supposed to extend eastward to cover the whole Konamuna, so you can see the outline in black. This is a border to New South Wales, and during the pandemic, we weren't able to cross any state borders, so hopefully that will be acquired soon. You can see this is a 10-kilometer depth slice on the left, so you've got this really conductive region. So this is in parts more conductive than 1 ohm meter. So in a region that's almost cratonic, so it's paleo to meso-proterozoic in age, that is sort of astoundingly resistive, conductive, sorry. And on the right, here we're at a depth of 40 kilometers, and you've got this conductive region. It's shifted to the west, so it's westward dipping, and we've got this big sort of conductor coming through here, and that's that feature that we saw in the previous Delamerian model. Having a look, so just going back, sorry, we've got this conductor that comes through here, not conductor, transect that comes through here, and here we can get a higher resolution look at this. So this is 2-kilometer site spacing of the broadband data, and you can see that we've got conductor going down to sort of 30 kilometers or so, up to about 10 kilometers or shallowing in the east. And pathways going up towards the surface. So this is quite similar to, actually, sorry, I'll just jump to this slide first. So this is an old model of that profile. So ignore the model, the details of the model itself. It was when the survey was sort of partially collected, but you can see the huge increase in resolution across the same profile going from AusLAMP to this new broadband array, so broadband transect. So that's sort of generally where we're going a lot in Australia now, in the areas where AusLAMP is complete, collecting these infill transects. But what you might see is sort of similarities with that Olympic Dam model. So these pathways typically are regions that may be prospective for mineralization. But in terms of, I guess, the main conductor of the Konamuna province and what might cause it, Ben Kay at University of Adelaide recently published a paper in Gondwana Research just earlier this year, and this is using results from a 2020 paper about the Lomagundi Jatuli event. So this occurred 2300 to 2000 million years ago. And what this graph is showing is the parts per thousand of the carbon-13 isotope of carbon in carbonate. So you can see as we're moving with time on the x-axis from 3,500 million years ago to today, we've got this sort of, general sort of similarities, but then you reach 2.3 billion years ago and we get this huge jump, which is known as that event. So the reason that the the amount of carbon-13 is going up in carbonate is that what this means at this time is that there was more organic carbon going into the ground. So rather than carbon sort of going into carbonates, it's preferentially sedimenting as organic carbon. And so this as well is associated with the Great Oxidation event, where there was a lot more oxygen available because the carbon wasn't going into carbonates. So there was a lot of oxygen then in the atmosphere from that time. This is actually as well at the same time that a lot of Australia, so Australia at that point was in part of Nuna, where we had mostly just the Western Australia, Northern Australia, Southern Australia craton. This region through here, these red regions, were all thought to have been connected at the time. So we've got, these are all associated with sort of major conductors. So we've seen the Konamuna conductor already, the Eyre Peninsula anomaly I pointed out briefly on the AusLAMP map. And then up here we've got, this is an anomaly, the Mount Isa anomaly. And these actually all are associated with Paleoproterozoic suture zones. So at the same time, so in that 2.3 to 2.2 to 1.85 billion years ago is when all of the crust was sort of amalgamating at the Australian margin. So we think that this, these major crustal anomalies are all a result of this, this major event, where it is extremely conductive, and that's why we interpret seeing these major anomalies. Just checking for time, I think we're still going okay. So this is the last case study. So this is on the Eyre Peninsula and Spencer Gulf. You may recognize one of your own in this photo. Thanks, Jake, for coming over and helping us out. It was my one and only sort of marine MT adventure, and yeah, thoroughly enjoyed it, more than some of my other more land-faring colleagues on the trip, who one got off the ship and said, I'm never doing marine MT again, it's land MT for me. But I won't point out who. So again, going back to a map showing the Gawler Craton. So in the southeastern part of the Gawler Craton, we've got this Spencer Gulf here. So we've got the Eyre Peninsula jutting out here, the York Peninsula. We've got the Karari Shear Zone, which is a major sort of lithospheric feature through here. And we've got a lot of, this is part of the IOCG belt through here. And we wanted to know what's happening through here. This, just looking in the Spencer Gulf, this is where the site locations were. So it's just a transect of 12. So I don't have too many results to show for this one, but really it's a bit of a pilot study. While there was marine MT acquired in Australia several decades ago, it's been a long time since there has been anything. So we're very fortunate to be able to use the Scripps gear to do this with the support of Steve and Jake and Chris. And, hopefully it can be the first of sort of multiple projects to better understand the offshore continental region of Australia. Having a look at AusLAMP in the area, so this is where it's cropped to the coastline, but we've got this Eyre Peninsula anomaly. This is one that I said was associated, potentially the interpretation of that is due to graphite in part from the Lomagundi Getuli event. And then if we don't crop the coastline, you can see the model here. It looks like there might be a conductor here, a tip of this conductive anomaly through here. And this is actually the one that major conductive feature we were seeing in the Delamerian model. So it's a really interesting area, but I will show some brief results of that. Again, looking at the Eyre Peninsula, this is with the induction arrows. They're all pointing to this really sort of linear conductive feature. And we've done a transect through the middle here. So where my cursor is going, sorry, it's not marked on this map. And this is the results of the land MT. So this was published last year. And you can see that it's really conductive, generally sort of a lot shallower in the eastern part of the profile. The yellow and red dots are graphite deposits that are, I think one is being extracted and one is currently still a resource, and connected to this deeper feature here. And so to the east of this profile is where we're into the marine area. So kind of already covered everything in this slide, but this is just showing a cross-section through the AusLAMP model. Again, here's the air conductivity anomaly, the tip of that Delamerian conductor through there. And so with the magnetotelluric data, we actually ended up doing a reprocessing of the data. And as of yet, since the reprocessing, we haven't had time to go back and remodel it. So these are very preliminary results that I'll show on the next slide. But we intend to remodel using the significantly improved data. But what you can see here is we're getting a bit more information about, so this is a really resistive granite Donington suite. And you can see that sort of coming, dipping under the Spencer Gulf. So this is new information here. And again, you can see that Eastern Nakara Arc anomaly, which was that major sort of linear anomaly there. But stay tuned for results on that. Hopefully we'll be able to work on that in the coming months. I'll just skip over that, I think. And just to summarize, sorry, I just realized I haven't finished the first dot point, but we've used magnetotellurics to be able to image fluid pathways of the mineral system. Magnetotellurics is now widely used in Australia by government and academia to aid in exploration and to help understand the geology. And I haven't shown it here, but industry have now adopted the usage of MT at sort of the camp to deposit scale. So having that AusLAMP data set has really helped sort of encourage the sort of infill MT surveys. And this talk is certainly not supposed to be a comprehensive overview of everything that's happening in Australia. I could be here for probably 3 days talking about all of the different studies, but it is an overview sort of mostly focused on South Australia. There's a lot of different types of studies going on, such as groundwater monitoring, etc. So there's a lot of people to acknowledge, and I've just got a few here, but I'd like to just acknowledge the sources of the data. So from the state and territory geological surveys in Geoscience Australia, and logistical support from Geoscience Australia and some funding. To all the open source software that is being used, such as MTPy, 3D grid and generic mapping tools. The modelling was done using the National Computational Infrastructure under a grant. And of course, I'd like to thank the traditional owners and also the landholders for being able to access their land, and the field crew who collected all the data, and AusScope for the instruments. So that is all. Thanks.
Thanks, Kate. That was really impressive, and right on time as well. We got plenty of time for questions. If anyone would like to ask a question, just unmute yourself and pipe up, or just raise your hand. Did you want to say something, Kate, first?
No, I'm just glad to see you all here because I couldn't see any faces and it was very quiet. And I heard a story the other day where someone gave a whole webinar and didn't realize that no one was online. So
Chloe's got a question.
Hey, Kate, really great talk. Really good to see you. I was just sort of wondering if you had an idea of the sense of like the timeline from when you do an MT survey to when like minerals are actually started to be extracted.
You mean by exploration companies?
Yeah, and I guess I'm also, these are more like logistics questions, but like curious how that works when like the geologic survey, like a government entity is collecting the data, and then who gets access to that data, and how do like, yeah, actual companies decide who gets to extract there, if at all?
Yeah, and that's a really good question. Probably something I just take for granted because it was sort of my bread and butter for 5 years. So I forgot to mention that part. But so the way that it works is that, so the purpose of a geological survey, I'm not sure how it works in the US, but in Australia, is to, firstly, we're the custodians of data from any exploration company. So they give us all of their data that they're acquiring on their exploration leases. And we've got a sunset clause, so it's 5 or 7 years, where after that time, that will become publicly available to everyone. So you can access this through, in South Australia, it's through SARIG, the website's called, or Geoscience Australia has a national portal. And then the data that we acquire, we call it sort of pre-competitive data. So it's, I say we, I don't work there anymore. It's a habit I need to get out of. So no, I'm just going to stick to it. Acquire the data, and we make that publicly available to anyone. So any of the MT data and then the models after a point in time become available. And so that usually, you know, for example, AusLAMP, that'll cover a lot of different exploration tenements. So there'll be companies that already have that land. And so they might use that to then go and do their own surveys. If it's ground that isn't staked, then there's a competitive process for that. And then it's probably just a bit more difficult when you've got, you know, a particular study that you want to do in a certain, within one tenement. And then in that case, you just need to make sure that you know, there's another reason for that, not just to help out one company. In terms of timeframes, I guess it, you know, maybe it would be, you know, for a company that already had the tenement, then they could, I guess they would see the results from AusLAMP or from another study that we've done, and then plan their own study. And there are companies, the bigger companies will go and sort of readily use MT, and then the smaller ones tend to use the processes where we're giving out funding to support sort of innovative techniques, if we can still call MT innovative, which we probably can't. And then, so yeah, so maybe that's kind of a year to go through that whole process. And, you know, I'd imagine, I'm not sure many companies would drill based purely just on MT, so there'd be, you know, follow-up studies. So it's a very long-winded answer.
No, that was great. Thank you.
That's all right.
Steve.
Yeah, while we're asking non-magnetotelluric questions, Australia has been famously anti-nuclear and is also famously pro-coal. Yet Australia has a good fraction of the world's known uranium reserves. When I was a young geologist, it was about a third. Is there any change in attitudes since, you know, certainly in some quarters, nuclear power is seen as one of the solutions to climate change, energy redistribution?
Yeah, I must admit I'm not up to date on that debate. I think I would probably be aware if there was any significant change. So I'm going to assume there's no significant change in general attitudes. I think a lot of, yeah, perception is that it's very scary. You know, it's a scary energy form. So.
I'm going to sneak a question in here real quick, Kate. First of all, that was an amazing talk. I thought it was really great. I've seen a couple of those slides before, but some of them were really impressive. I particularly was impressed with the sort of infill slides where you sort of use the AusLAMP data to identify an interesting region, maybe an interesting conductor at depth, and then go do sort of a denser sort of MT line, and just the increase in resolution is really impressive. I was wondering how much MT is being collected by companies. So like doing that sort of a thing that you've done occasionally, sort of, you know, infill lines here and there. Is this being done like every day by exploration companies, or is MT still sort of like a niche tool for them?
I think it depends on the company. So for example, like I would say that I don't think there's any companies that would have someone employed who does MT. Maybe that's, not entirely accurate, but it would be close to none, within Australia. And it's done by contractors. So we've got sort of 3 or 4 main contractors that acquire MT data. And I know that they are always busy. So, it's certainly not on the scale of your other, more traditional techniques, but I think, each of those companies would have 20 or so instruments that are kind of almost constantly out. And so, like, I know, for example, in South Australia, BHP been using MT doing major studies. So BHP have the Olympic Dam deposit. So I guess when they've got the fingers of God in their backyard, it's quite convincing for them that it's a useful technique. But yeah, I don't know if anyone's actually sort of gone and done the analysis of the companies and, how much MT is actually being done across the country, but it would be really interesting to see it. But it's certainly picked up in the last sort of decade or two. Like, the more that we're using it and promoting it as a useful tool to navigate sort of the traditional challenges of exploration, the more people are starting to use it. And generally now, I think when I started doing honours, you had to begin each talk with like an overview of how MT works, whereas now it's pretty much everyone knows what MT is. So even just that alone is sort of a big increase in awareness.
I have one other question I want to ask. I just always feel bad jumping in as the MC. The other question I have is regarding the study you mentioned, or actually it was, I think, maybe 2 studies you mentioned that sort of had looked at correlations between either lithospheric thickness or conductivity and the location of mineral deposits. Like that, just the correlation, that was quite interesting. And I was wondering, now that we have pretty decent, especially in Australia, increasingly good understandings of resistivity from MT soundings and MT inversion, can you do sort of correlations between that and other geophysical methods and sort of try to like come up with 2 techniques, for instance, that both sort of see the same thing, or maybe a second geophysical technique that can sort of rule out false positives or false negatives from MT, or just help pinpoint locations of deposits? Is there anyone that sort of comes to mind yet?
Well, I think, just realistically, just over the sort of depths that you're looking at, really your only option would be passive seismic, but they're showing different things, whereas, in MT, the conductors are generally due to sort of minor conducting phases, which would be completely invisible to the seismic technique. Of course, any experts on this call, I'm aware that there's a lot of seismologists. Feel free to correct me on anything I'm saying. There have been some studies with using satellite gravity and comparing that to MT. So for example, that big conductor around the Gawler Craton, that curved one, that as well comes up in those sort of satellite gravity models. There is a project called LitMod, which is looking at doing sort of probabilistic inversion of MT, 3D MT, as one of the inputs into sort of a whole comprehensive way of looking at the lithosphere. And that project is quite advanced, but it's definitely something to look at, to keep an eye out for when it's sort of fully operational.
Thanks.
But yeah.
Oh, sorry, go ahead.
Yeah, I was just going to say, yeah, you can put, seismic data, geochemical data, MT. So I think MT has been the sticking point. That's been the most difficult part, to get that information to be able to sort of line up with all the various other data sets that go into it. But I believe they may be there now. So Cotti, Constanza, Manacero in Eastern Australia. She has just recently finished a PhD doing sort of the 3D probabilistic MT inversion code, which is to be input into LitMod. So that's, yeah, a pretty amazing step forward. But yeah, don't know too many details about that.
Thanks. Any final questions? We're coming up on the canonical hour pretty quickly. If not, let's thank Kate once again for getting up at 4 in the morning to talk to us. That was a really wonderful talk. I really appreciate it. And we'll see you all next week for our final seminar of the term. See you around, everybody.